Okay, next up is Mike's going to talk about cold dust and dense cores associated with H2 regions.
So a few years back, Carl signed my thesis, and Berkeley awarded me my PhD. But I really didn't feel my thesis was done. I was a little rushed, not by Carl. Okay, Carl didn't rush me at all. I had a wife who'd finished her PhD at Berkeley, finished her postdoc, moved to Seattle, taken up a faculty position. I kind of had to finish up, so I did. But I didn't really have my thesis finished, and so I've been working on it since. What I'm doing now is I'm giving Carl a status report on the current progress on my thesis. The rest of you are welcome to listen in on this, but I thought he might like to hear where we're at. Now, the first part of my thesis was a survey for H2 regions in the outer galaxy. I used the 85-foot. I did this at 6 centimeters. And I really wanted to continue that survey. I really wanted to go deeper, and I hadn't quite covered the entire area. Shortly after I left Berkeley, a year later, I think, I got this dramatic email from Carl. Many of us in here remember this email about this dark and stormy night where he drove up and discovered the 85-foot in ruins on the ground. So the first half of my thesis was done. The second half of my thesis was doing something with all these H2 regions. And at that time, I hadn't really had time to reduce all the radio data, so it was mostly focused on the optically visible H2 regions. And I'm going to talk about that part some more today. There's been lots of new stuff. Now, what I'm going to really talk about, though, with that is from the Scuba 2. So here's a picture of Scuba 2, just after we opened it out of the box, uncrated it at the JCMT. Carl probably doesn't know this. I'm sure he doesn't know this, but he's partly responsible for the creation of Scuba 2. You didn't know that, I'm sure. Because as a student, whenever I wanted, the 85-foot didn't do what I wanted to do. I needed things on the 85-foot to make it do my survey. And whenever I asked Carl to buy something, he'd say, "You could make that." So I spent months in the machine shop and in the electronics shop building equipment. Now, somewhere in the 90s, actually much of the 90s, I spent on, I had many other projects, but one of my projects was studying dust in elliptical galaxies, looking at the emission at far infrared and submillimeter. I used IRAS, not much, I did a little bit of work with IRAS, still not really fill that up well. I used the UKT14 single pixel detector in the JCMT. I used Scuba 1, did some work with ISO. Really, there was no instrument that I could go beyond that. We'd really hit the limit at that point, and I really wanted to look at more of these things. I got to chatting with Wayne Holland in the UK, and he had this new detectors, these TESs, and he wanted to go ahead and build this for JCMT, but the JCMT Instrument Development Fund was at zero. There was no more money left. The UK had indicated, that was PPARC at the time, it indicated that they were not going to fund this. So I said, what if I build half of it? And would PPARC change their mind? And it turned out the answer was yes. I wrote a grant proposal in Canada, and PPARC funded it, and we built it. This was supposed to speed up mapping from the original Scuba by at least a factor of 100, potentially as much as a factor of 1,000. So as a co-PI, I have to show a few things. I have to tell you a little bit about it. On the left was the original Scuba, 10 hours on the Orion filament. Just after we turned on Scuba 2, before we'd optimize anything, before we had the software, 24 minutes, and it's a bigger, more sensitive map. The software wasn't quite as good to show all the resolution there, but it was way better. It was already a factor of much, much better. It's now, in the last year, which is 3 or 4 years after we started actually operating it, we've really got the software, the pipeline. We're quite confident we know what we're doing. We're about 250 times faster mapping speed than the original Scuba at this point. So a huge speed up. We were hoping to get 1,000, but we didn't quite achieve that, but we did meet, past the factor of 100 goal. And for this meeting, I thought I'd throw in Poll 2, which is also part of my side of the Canadian contribution to this. My grant paid for this, and this is now available for general use. As of just a few months ago, the last round of proposals that were due in March, you could propose to use this. And it is working, the software. This, by the way, is also, the PI for this is Pierre Bastien, who was mentioned earlier in Alyssa's talk as a polarimeter with photomultipliers back in early 80s, I think. Here's two maps. that I just got sent last week by Simon Coudet, Crab, and Orion, and I think this Orion magnetic field, slightly different data reduction, is out on the poster that Jason showed yesterday in the poster brass. So just that's available. I'm not going to talk about polarization measurements at all. I have older stuff. So what was it that I was doing? What was, the second half of my thesis was, looking at H2 regions and thinking of things you could do with them, all this big sample of hundreds of H2 regions. One of the things that I thought, I'm not going to read through this at all, was that all these H2 regions, the optically visible H2 regions, are the evolved, older H2 regions. If you're going to understand, if you want to learn more about how massive stars regulate star formation, either enhancing star formation through some collecting collapse model, sweeping up clouds, or by being warm and stopping star formation, you should look at the older ones. And so those are the ones that are generally visible in the optical. And so I have been doing, amongst many other things, looking at these. And so here's some of the things, and there's many more listed in this paper by one of my graduate students, former graduate students. I had a whole series of graduate students who had the title H2 region, the words H2 region in their thesis title. Just my thesis title was H2 regions of the outer galaxy. So not all my students have done this kind of stuff, but quite a few. And again, I'm not going to go through all of these things. It turns out that there's a lot of problems. There's a lot of difficulties you have to overcome to get the science out. And I'm just going to mention a couple of these. I'll go on and just do a couple comments about a few of these with the next few slides. But these issues are all, there isn't a thing up here that can't really significantly change your results if you don't get it right. And in particular, the one that we talk about a lot is the very first one, the dust emission. What is beta in the dust emission? This is mostly a diffuse crowd here, so I'm talking about the dense ISM and the standard problem in doing dust. And let me just point out, we have a 450 micron and 850 micron detectors. So I have images at both 450 and 850, and you can do a flux ratio of that, which should relate directly to temperature, but also to other things. But part of getting temperature is knowing what value of beta to use. If you have a third wavelength, you could constrain beta. And there's some work that we're doing, other people have done. So there's a number of different curves of what your observed flux ratio on the left versus your temperature. Notice at low temperatures, it doesn't make a huge difference. All these lines converge. If you have a very high flux ratio above about 10, then it's not thermal. There's some other things in there that are really causing problems. They're enhancing the 450 or depressing the 850. Or another version of this, notice that this is low temperature total flux density. So here's two very different versions of beta, but they give essentially the same flux ratio. Everything's normalized to the 850, so this is really a flux ratio here. Notice that the two lines in the middle, there was a pointer, right? These are 8 and 10 degrees, different beta, and they're about the same flux ratio. This is 15 and 30 degrees. When it gets warmer, a difference in beta can make a factor of 2 difference in the temperature. Okay, down here it's only 20%, down here it's 10% difference in temperature. So hot temperatures are very uncertain. You just know they're hot. Well, hot, I don't even think that 15 and 30 is not hot. That's warm. Here's what the images might look like. Here's one particular field, the sharpless 156 H2 region at 850 microns. The whole field, I'm not going to spend much time on big entire fields. I got a few of these pictures. Notice the noise is somewhat higher around the edges. The H2 region's about here. I'm going to zoom in a moment, but first let me show you the 450 where the noise is somewhat worse, the sky is worse, and so the noise is somewhat worse, and we don't do anything on the outer edges here. And this is this is Jansky's per beam, sorry. So zooming in on that object, I put a star here. This is the 850 micron image zoomed in. This is the 450 raw image looks much better. The resolution is much better. This is being convolved with all the various beams that are involved, the error beams of the 450 and everything. This is a matching image. This is what we're actually going to measure the temperature from, using that and a similarly convolved 450. Here's a visible image overlain on that. I think this is the DSS image, perhaps. So you can see where the H2 region is actually located, the optically visible H2 region. And that star, in fact, is the exciting star. In fact, I'll throw in one more polarization image, old one from 1983. It's turned 90 degrees, but you can see this is just this dust scattering. the starlight from star 1, which is the exciting star, and there's a fairly large degree of polarization in just the scattered light from that star. And I put this from the same paper because it just beautifully illustrates all the objects I'm looking at are things where the H2 region is very visible. It's not behind the cloud. If the observer's off on the left, the H2 regions are in front of, or maybe there's no molecular cloud in the middle, but there's not much in front. Part of my thesis was looking at the extinction towards all the optical H2 regions. It was on average 3 or 4, almost independent of distance. At 5 kiloparsecs, the extinction was still 3 or 4. They're looking through a hole, and done. There's also VLA observations, and so you can see where that is. That matches up. Here's that object again, just for a moment. And one of the other things I mentioned as a problem is that there are various other things that contaminate these continuum bands. In particular, the CO3 to 2. And if you probably can't read the numbers, but the peak flux in the 850 is about 1 Jansky. The peak flux, if you convert this into the same units, it's about 0.1. So it's about 10% contamination due to the CO. It changes from one place to the other. Some places it's as much as 25%. Another thing that is there is contamination from free emission, because there's an H2 region there. So you need to deal with those things. Here's what you actually observe when you do the flux ratios. All the corrections put in. Here's the flux ratio, 450 to 850 in colors, and you can see the flux ratios up to about as high as 9. These areas around the edge are the places where the noise is large, so it probably, noise don't really necessarily believe the flux ratios down here are very accurate. There's where the star is. Notice the flux ratios are slightly higher to the top, to the right. The flux ratio, which goes with temperature, peaks here, not on the peak flux. It's just slightly offset. Convert that to a temperature, and the thing that stands out here is that it's mostly blue. Blue is 15 degrees or colder, the dark blue. There's some light blue. There's some area up here that's 25. So just flipping through, I've got about 50 of these pictures. I'm not going to show them all. I'm just going to show 2 more slides with a few of them. And we've got about 100 of these cores, like this one here is a cold core. Temperature is about 8 degrees in that core. So there's a few more just made small. I think the thing that stands out in these is how much blue there is. Lots and lots of blue. Here's another cold core. No, there was, oh yeah, here's a cold core surrounded by warmer gas, but again, it's at where the noise is bad. And here's a warm core. It's a dense core, but it's warm, so this is a likely candidate for a protostar. This one up here is very hot, looks very strange. I'll just point out that object, sharpless 254 to 258, with very high densities and very high temperatures, is this object. I combined a VLA survey I did for H2 regions a while ago. All the red is VLA. That dust from Scuba 2 is right here in between these really big H2 regions, the obvious place where the H2 regions are really dominating what's happening in the cloud. Really a big push there. And yeah, okay, so again, I'm just whipping through a few things. Here's a well-known collect and collapse model H2 region. It's been well studied, sharpless 104, nice round. I particularly put this in for Carl because he likes bubbles and things like that. And here's another one that's not so well studied. People haven't really thought much about it. That's the original 850. Let me just zoom in on those. And there's the ionized gas, and here's where the Scuba 2 emission is, the ionized gas, the Scuba 2. These are kind of similar kind of things. Notice there's not very much emission. I've looked at various Spitzer bands. These ones, unlike some of the other ones, many of the other ones, don't show much Spitzer, pHs and things like that. Some do, are very, very strongly. In fact, the one I showed earlier had that. These are surprisingly cold. There's one hot spot here in all this dust around this one. There's one hot spot down here, but it's pretty cold in general, even in these collect and collapse. Dense cores, pretty cold, below 20 K. I'm just going to flash this up. I'm not going to try to do any of the analysis here. This is intensity versus radius, showing that we've resolved the cores in most cases. And you can take this. This is very preliminary work because we've only been able to do this for about the last year. We've been confident in the pipeline. So this stage of reduction is very new. But you can do things like you can convert the intensity versus distance radius into volume density. This is not meant to be a fit. This is just what a Bonner-Ebert curve might look like, with a turnover. That's something we need to fit in the future. And just a quick summary. The main thing, I think, is the main points are that there's a lot almost all of the dust, except for a few hotspots, is below 30 K. In these regions where you think that the H2 region has had, these are the H2 regions that would most impact, show the most impact on their surroundings, that the H2 regions have had chance to expand, to shock, to heat with photons, shocks. But most of the dust is below 30 K. Only about 10% of these have dust above 30 K. Many of these have cores, probably on the order of about 60% have cores that are below 15 K and dense cores. So cold cores, it's in a place where you might think the feedback might generate more warm material. These are bigger than, I'm also working on Gould's Belt survey with Scuba 2. It's a big team doing that. And there we find lots of cores that are around 1 or 2 or 3 solar masses. These are not them. These are tens of solar mass cores, hundreds of solar mass fragments of clouds. And, but the results are very sensitive to the input. Thank you. Chris. Sorry, that's your turn.
Yes, I have a question about beta. The extragalactic astronomers used to go ahead and try to fit beta, and they would get strange values. But then it was realized that as soon as you allowed for more than one temperature, then you could fit the spectra very well with a beta of 2, which is what you expect theoretically. So could you comment on that in the case of your application?
Well, so it doesn't make very much difference for beta 2, it turns out, because all my clouds are pretty cold. So the things I've told you about these results are generally, it doesn't really matter. There's only a few hotspots. And for me, the difference between it being 60K and 40K, it doesn't make for me, again, a big difference. So the science results here are not greatly impacted by beta. But of course, I can't really fit beta with just the data that I have. I have to either choose temperature, a single temperature, and assume a beta. The other, because I'm fitting column and temperature already. And the other thing, of course, we do have an FTS, and there has been some work done on that and using that, because then you can actually fit to beta as well. And there are indications of beta, a wide range of beta from down at 1. In fact, my favorite quote on this is Xander, who says, every different place you look, the dust is different. So there's no uniform.
No, but if it's not isothermal, then
yeah,
that changes it.
Yeah, but I can't. What can I do?
Okay, we're out of time for questions. If bring your questions to Mike at a break. So let's thank Mike again.